Hello, good morning, good afternoon, good evening, whatever time zone you are on. Welcome to our Open Lakehouse plus AI mini series. We're coming to you live from San Francisco Bay Area, but we are broadcasting it live on different channels. So we are live on YouTube, X, and LinkedIn. My name is Jules Damji. I am part of the developer relations team here in Databricks and focusing on open source projects like Spark and MLflow. And joining me today is my esteemed speaker, Niranjan Nataraj. Niranjan, you want to say hello?
Hello, everyone.
And he's hailing all the way from Austin. And in some way in the background, I have my esteemed program manager, Carly, who brings us all this live to you so we can actually be globally connected. Now, a couple of logistics before we actually get started. We can't hear you. This is sort of a one-way broadcasting, unfortunately. So we ask you to somehow keep your questions coming in the chat on your right-hand side, whatever channel you are logged in. Tell us where you're hailing from. Are you coming from a different part of the world, since this is a worldly event? So let us know where you're hailing from. And if you have any questions, we'll try to address them towards the end, given the logistics. So we'll have Niranjan give a talk first, and then we'll reserve about 15 minutes, 10 to 15 minutes at the end, and we'll address your questions. So those are kind of the logistics. Now, today's talk is about how Spark plays a role in doing your AI workloads, managing large metadata. Now, if you have dealt with building large lakehouse, there's a plethora of ecosystem projects that come into the umbrella of Lakehouse. And these are some of the open source projects. And today we're going to talk about Spark, how you can actually handle all the AI workloads. And when you deal with AI workloads, a lot of images, there's a lot of metadata associated with that, and it becomes a bit a management problem. So Niranjan is going to show how you can actually accelerate some of those workloads using RAPIDS and GPU accelerated accelerators, and at the same time manage the metadata at scale. And Niranjan is the senior manager in the accelerated processing and ML platform in NVIDIA. He has had about 15 years of experience working in NVIDIA, so you're going to hear from the horse's mouth. Given that, I'm going to hand it off to Niranjan, and please, Niranjan, take it over. And for you, keep the questions coming. We would like to hear where you're hailing from, and welcome again to all of you. Thank you. Niranjan, take it away.
Thanks, Jules. First of all, thanks to Jules and his team for providing me this opportunity to present today. And thanks to all our audience joining from various parts of the world. I promise you, at the end of this presentation, you will learn something. You will have something to take away home and think about how you can leverage some of the things I talked about at your workplace. Hopefully, it will improve the performance, cost, and you'll see some benefits. So let's get started. So the talk today is about GPU accelerated Spark based data processing, and we'll mainly focus on metadata management for GenAI workloads. So the agenda for today is we'll start with an introduction, brief description of what problem we're trying to solve, what is the problem, and we'll continue to look into some of the use cases where this problem is applicable, and then finally we'll address how do we solve this problem with respect to data processing, orchestration, and architecture. So let's begin with the problem statement. To think about GenAI, we generally start with raw data sets, and these raw data sets are really huge. It's in petabytes, exabytes, and so on. And our goal is to get this raw data processed as soon as possible so that it's available for our model training workflows to run on GPUs and churn out the models. So we want to keep those GPUs as busy as possible, fully utilized. There are hundreds or thousands of them being used, and we want to deliver the best models to the end users. So the GenAI data sets consist of both structured and unstructured data. It's predominantly unstructured, like images, videos, text files, audio files, etc. And then on top of that, the challenge here is these data sets constantly change. The features, the metadata, they are always rederived, recomputed, and this will result in newer data sets, refined ones that we use for either foundational model training or fine tuning. The other challenge also want to highlight is the data and the compute are sometimes may not be co-located. It may not be true for everybody, but here at NVIDIA, it is something of a challenge that we see. So it's widely distributed across different data centers, different regions, and there is also data sovereignty and compliance where because of which data can be highly distributed. So if you look at this picture on the slide, so to the left we have the raw data, and to the extreme right we have the model. And our goal is to optimize this end to end. So far, I think a lot of focus is on how do we accelerate training, how do we accelerate inferencing. But sometimes before that, we need to accelerate the data pipelines. And in a lot of cases, what we have seen, and we have gone through this journey as well, it runs on CPUs. And into today's talk, we will look into how can we accelerate the data pipelines as well. So the kind of the problem statement is, okay, if we have hundreds and thousands of GPUs waiting to be fed training data sets, and even if we can get 5 minutes faster churning out the running the data pipelines and make those data sets available, it's still a lot of savings in terms of keeping those GPUs fully utilized. So that's kind of the data problem, and we'll heavily focus on this gray box today. How can we accelerate them? What are the technologies we can use? And then let's transition into a specific use case here. So let's double click on the data pipelines part. What really happens there before we get to the training workflow? So so let's start with the data acquisition part, and then all the way up to the fine tuning. So with data acquisition, generally we have data from the internet or from the vendors. And this goes through the regular data ingestion workflow process, which is stored on the object store. So it can be raw formats of images, text, videos, and sometimes this also involves generating synthetic data, and that can also be part of the data acquisition or data ingestion workflow. So once we have all the raw data, this it goes to box number 2. So I'm just labeled it for easier comprehension. So here in the box number 2 we have metadata processing workflow. So what really happens is, okay, we have all this data, we need to make sense out of it. What do we care about? What does it look like? Do we have what's the size of the images? What's the language of the audio? How do we break this down into multiple clips? How can we add some bounding boxes and recognize the objects? Where are those objects in the file? So all this data we need to capture as part of metadata processing workflow. And then the most of the data that we capture here, you can think of it like structured data. So it has we know what we are capturing beforehand. So we can store all that information in a structured format on, again, an object store. This is the raw metadata. And then finally, we can convert that raw metadata into some curated metadata data sets through some ETL. And once we have the curated metadata sets, this is where the users come in and explore the raw data. What is the raw data telling us from the metadata? And this generally happens using either dashboards or reports or some sort of analytics. And once the users decide, okay, I would like to train models or fine tune a model specifically for stop signs. So you write a query that says, okay, let's get a list of all the videos that have stop signs in them. And you retrieve the metadata, and that metadata contains pointers to the raw data that exists on the object store. So now you feed that into a data preparation workflow. So now this data preparation workflow will identify the raw files and then convert that into a fine-tuning data set, and this data set is fed into the fine-tuning or validation workflows that will create the models. So this is kind of the entire flow. It involves ingestion, it involves processing, it involves retrieval, and finally fine-tuning. I think for the most part, we have figured out, okay, fine-tuning, it's all GPU accelerated. Now let's talk about ingestion, processing, and retrieval. How do we accelerate that? What does it take to accelerate specifically box number 2? This is the primary use case, and this is kind of a life cycle of most of the generative AI workloads. And to specifically give some examples, here at NVIDIA, we are following this process where we have a workflow for each stage: ingestion, processing, and retrieval, and model and fine tuning and release. And this is an example from build.nvidia.com, where our users are following this process. They have released several models here, which can be deployed as a NIM. It's specifically focused on speech to text, but there are other examples like Cosmos Reason, which is a visual language model. So users fine tune those VLMs, say for example, to train robots in a physical AI world, or they train or they fine tune those models for warehouse operations. So this is applicable kind of in a generic way for most of the generative AI use cases. Now, going back to this use case, just doing a deep dive into box number 2, which is mainly data processing, and how do we accelerate this, right? So let's break this down into compute and storage, and we'll address them separately. What's the compute we can use, and what's the storage format that we can use for ingestion, processing, and retrieval. So starting with compute, I want to introduce everybody to GPU accelerated Spark Rapids. And the notion here is, okay, we can accelerate data processing using GPUs. GPUs matter before model training. And the main use cases here are, okay, where all do we can use Spark, right? Document parsing, feature extraction, any large scale joins and aggregations. All these can highly benefit from using accelerated compute. And here we are saying Spark Rapids is one of those compute engines which can really speed up to 5x with Spark batch workloads, or reduce the cost by almost 30%. We have seen speedups up to 100x with Spark ML. And the best part about this is there is zero code change from CPU to GPU. So if you already have the Spark code running on CPUs, there is absolutely no code change. You can just enable Spark Rapids jars on your clusters and spin up the GPU executors without any code changes. You can seamlessly switch from CPU to GPU, and you should be able to see up to 5x speedups. So here is a real example where our users have some large-scale joins and aggregations. I think this is mostly a large-scale join. And here, what we're seeing is, okay, we want to run this query, identify some pointers to the files that specifically deal with certain aspects of the fine-tuning. And we want to limit it to 900,000 size of data set, for example. This query takes around 1 minute, 28 seconds on GPUs with 20 executors. I'll show a quick demo in a minute. And the same query takes around 4.5 minutes on CPUs on 25 i7 i4X large nodes. So real quick, just switching screens. So here we have a simple cursor editor where we can connect to the Spark clusters. We have our own internal implementation of Spark Rapids as a service. It's called NV Spark. So this code will connect to the clusters running remotely. And here I have a cluster set up with 20 executors. And this is just to make sure that the cluster is up and running. And as you can see here, each of the executors have one GPU. It might take a while to connect, so I knew this might happen, so that's why I added a screenshot, and also ran some of the queries beforehand. When we ran this query recently, just this morning before the presentation, it was taking around 1 minute 43 seconds. So the same query on CPUs with 25 executors, it's taking around 4 minutes 5 seconds. This is a production table on which we're running queries, so the times vary quite a bit. But yeah, here is the 20 executors, and we have a cluster running, so we can run this query. I probably will not wait until this query finishes, but just wanted to show that, okay, this query runs, the same query runs both on CPUs and GPUs without any code changes. Yeah. Switching back to the presentation. Uh, there was also a talk a couple of months back from Spark Rapids team in the same forum, where they talked about Spark Rapids a bit more in detail. So please refer to the talk. It has a lot more details on how to leverage Spark Connect with Spark Rapids. So it's pretty interesting. It will help you get started quickly. So for compute, we would like to leverage Spark Rapids because it natively runs on GPUs, and we can see up to 5x speedups. Now, switching to the storage side of things. Okay, why? What is the structured data sets, right? Because all the raw data is actually unstructured, a majority of it. So where is the structured data coming from? So here's where we collect a lot of metadata to understand the unstructured data sets. And the main use cases here are, okay, we want to be able to track dataset versions or lineage or some of the attributes of the datasets like caption, language, author, clip duration, etc. And this is where structured datasets come into picture. And uh, generally, we have either human annotators or AI assisted labeling to look into these datasets and generate the metadata. And this metadata is not small, because you can you can generate so much metadata from this for every iteration. Currently, our metadata size is close to 3 petabytes and growing. And one of the things that we found is, okay, we can either store this on object store as Parquet or some other format. But what we really found useful was storing it in a Delta Lake format. And the reason why we chose Delta Lake format is it has asset guarantees, it's transactional, it allows for time travel, it has ability for concurrent reads and writes. So we can easily version the data sets, we can track the lineage, we can cater to large scale tables of terabytes or petabytes of size on object store with Delta Lake format. Here's an example of what it would look like. So we have a unique ID that points to a source of the data. And then we have some metadata like caption, URL, language description, and the clip duration. So any user, if they want to train something on, say, Spark Rapids, just give an example, they can just write a SQL query that will go and fetch all the source links for videos that are related to Spark Rapids, right? So it makes it very easy for users to interact with metadata and indirectly on visualizing what's there within the unstructured data sets. So now that we have established, the Delta Lake is a good candidate. There might be others as well, like Iceberg. Spark Rapids also supports GPU acceleration on Iceberg. So there are a couple of options there. Now, one of the things that we highlighted at the beginning of this presentation was, okay, there is a problem where the data sets are constantly changing. So new metadata gets added, existing metadata can be corrected anytime. And based on the use cases, what we have seen is the retention for all this is very high. I don't think we have set retention right now within NVIDIA, because it's all additive at the moment, and um, it's growing, right? So one of the things that we found really useful was having this medallion architecture for handling metadata. So users generally, or AI assisted labeling generally sends the data to a queue or to object store, and from there we process it through three stages: bronze, silver, and gold. And bronze is mainly just consuming in from the queue as soon as possible. It's just like a pass through. And then we run another job that will consume from the bronze table, apply some transformations, filters, does append or merge, and finally we aggregate and do some joins on multiple silver tables to create the gold table. This process entirely runs with Spark Rapids on Delta Lake, so kind of GPU accelerated Delta Lake. And finally, our users are able to query the gold tables and build some dashboards. And also, if they want to automate querying the metadata to create training data sets, so we have exposed some APIs for querying the gold tables. One of the things that we explored was, okay, do we really have to go through this three-stage process? Why don't we just shift left? Because our goal is really to get as soon as possible from raw data to model, right? Um, One of the things that this process, medallion architecture, serves is flexibility, in terms of we can actually recompute silver and gold tables many times. That way, we don't have to store the raw metadata in the queue or object store for longer time periods. And this is very helpful. But ideally, someday, hopefully, we have some way where we can reduce the number of stages. We do in some cases where it's not, where we know that we don't have to recompute a lot. But it would be ideal if we can reduce the number of stages. So uh, now that we have the goal tables, what do we do with it, right? So this is where retrieval and analytics come into picture. So we have created dashboards. Users build these dashboards to see what's going on inside the unstructured data sets. And now they can decide, okay, so today we want to train models on, from for English to Spanish or vice versa. So how do we write a query to pull all the relevant files needed to build the training data sets? And this is the retrieval part. Now, putting all this together, we talked about ingestion, processing, and retrieval. And we also spoke about compute and storage. So now users need some uh, easy way to uh, c- uh, do ingestion, processing, and retrieval. We don't want them to go configure clusters for each stage or worry about infrastructure. So this is where our APIs, serverless APIs, come into picture. So for each of the processes, we have an API or sometimes a set of APIs, depending on the use case. So we have something called bulk upload, because we noticed that data arrives in large chunks. So for example, if we want to collect more data for stop signs in a specific city, um, our AV team can drive around the car for several days or weeks, and then come back to the garage and uh, upload the data to to object store, and from there we extract the raw metadata in large chunks. So this is where this bulk upload really helps. Bulk upload can ingest data in large chunks very quickly. and make the data available for our users so that they can continue with the training process. Then next is data processing. So this involves change data capture or regular batch ETLs or materialize. Materialize is like a special API where you can just create a view um, or select a subset of data from a table and materialize that periodically. So this will really help create those gold or platinum tables, for example. And finally, for retrieval, we have a low latency API to query from various lakehouses. So this is the query that really this is the API that really simplifies. Okay, get, curate a set of files that have uh, so some warehouse operations related uh, videos in them, right? So that's the DRS. DRS is the data retrieval service, and it will output the results in Parquet into some directory, and we can use that to now build our training data sets. All the APIs run on provision underneath Spark Rapids GPU clusters, so that way it's all end-to-end accelerated. Now, one of the other things with respect to GenAI workloads is data is flowing across the platform in at various steps, and we want to be able to orchestrate all those steps in a single workflow. So it's like a DAG of heterogeneous tasks from starting from ingestion, processing, and retrieval, right? And finally fine tuning. So how do we do this? So here is where we use Kubeflow, and we use Kubeflow pipelines for orchestrating the DAGs. And we have built some reusable components. If you're familiar with Kubeflow, that's kind of the nice feature that they have, where you can implement your own custom components and significantly reduce the number of lines of code that developers have to write. Or you can even have these reusable components to completely abstract all the Kubernetes construct from data scientists or data engineers. So here we have a simple torch reusable component where users can just specify uh, uh, how they want to train, how they want to fine tune their models. And then in the next one, we have a NVSpark component. So this is where we have simple users can write some simple Python notebooks, and they can execute that on GPU clusters. Um, and finally, if we put all these things together, the APIs plus the fine tuning jobs, the reusable components, we have a workflow, and this workflow can be executed periodically or based on some event based trigger, so that we always have the fastest execution of workflow that will feed the training data sets to the GPUs. Okay, so far we have looked at how we are going to accelerate the pipelines. Now going into the implementation part, what's the architecture behind this end to end? And let me start with a high level overview of what the architecture looks like. And here uh, we kind of follow a pancake architecture where we have like 4 layers. At the very top, we have the users. We want the users to just focus on their business logic over plumbing. And we expose some REST APIs that I showed earlier. And also we provide highly optimized containers for fast development and deployment. And these users interact with our services like Workbench or NVSpark or Workflows. And these are the managed services that we run on top of Kubernetes. Um, and we have the Kubernetes layer that abstracts the underlying infrastructure, a GPU accelerated infrastructure, and this can be run anywhere. It could be on DGX Cloud, or it could be on any CSP, or and works with any object store. It's very easy to deploy. As I mentioned earlier, our use cases are kind of diverse, distributed in different data centers, in different regions, different CSPs. So this architecture kind of makes it very flexible to deploy this whole stack anywhere. So Going one level deeper into how the managed services are implemented. So here we again separated the managed services into control plane and data plane architecture, or the compute plane. And the users generally communicate with compute plane or control plane using the BI tools, CLI, or their favorite IDs like Cursor or Jupyter. And the control plane is generally used mainly for authentication, authorization, or running the API server, anything that can manage multiple, any service that needs to be there for managing the multiple compute planes. So on the compute plane itself, which is the most important part, this can be deployed on any Kubernetes. And the storage is, think of it like Lakehouse, which hosts both structured and unstructured data, and this is where all your structured data sets are in Delta Lake format. So to the right, we have this NV Spark. NV Spark is simple Spark Rapids as a service implementation within NVIDIA. It makes Spark cluster management fully serverless for our users. And to the left is the services from Kubeflow. And here we have some additional customizations that we have developed, like image caching for faster cluster startup times. We also enabled advanced scheduling algorithms like Volcano plus bin packing, so that we can increase the utilization of GPUs. And overall, for users, it's mainly fully abstracted. They don't need to worry about infrastructure management or what kind of how to size their clusters. We try to t-shirt size as much as possible. And we also try to optimize as much as possible in terms of auto scaling or scale to zero. And this architecture is kind of very flexible, because we know that a lot of companies have their own way of orchestrating workflows. And and since this is all Kubernetes native, it's very easy to adapt with their existing stacks as well. Okay, so finally, we are looked into the architecture. We know how to solve. We know where Spark Rapids will help, where Delta Lake will be useful for GenAI workloads. Eh, we know that GenAI foundation is data engineering, and we want to unlock scale before training using GPUs. And Spark Rapids is a good option that will speed up data pipeline workloads. And we also need a way to store and process metadata, and that's where Delta Lake comes into picture. So consistent metadata and reproducibility with good orchestration of DAGs helps build trust, and we can easily visualize, okay, which model came from where with those workflows. I have added some additional references here on Spark Rapids, so feel free to explore this, and this will help you get started very quickly. Okay, that's all I have for today. So any questions, happy to answer them.
Thank you, Narajan, for this very incisive and detailed architecture about how you guys are actually managing, all the data management and all the images that actually come at massive, massive scale, and the infrastructure and the architecture is quite impressive. Waiting for some questions to come in, but I had some questions while you were actually presenting. I saw you have adopted the medallion architecture, which has kind of become the standard how we actually do data processing ETL, and it's good to see that you're actually adopting that in the scale at which you're actually doing for your AI workloads. How many distinct silver tables and gold tables do you have? And the follow-up question would be, what determined or what factors made you decide to have X many distinct tables? Was it the anticipation of how users might anticipate or query distinct parts of the workload images or the metadata they wanted? Give me some insight into what was the criteria to decide, okay, we're going to have 5 tables or we're going to have 25 tables, and this is the reason why.
So So different workloads have different needs, and it's very dynamic. For example, like I was giving examples on with respect to warehouses or robotics or speech to text, right? And when users begin with, they will have a very specific use case in mind. Like, okay, I want to collect metadata, and I'm only interested in knowing about all the audio files that have just Spanish as the language, right? They begin with that in mind, and then they execute that and end to end. Then they realized, oh, okay, maybe there is something else that I need to collect. Maybe I want to chunk the clips a bit better. Now they'll come back and say, okay, do I go update the same table? Is it possible, or should I just make it separate table where I have information about language in one table, information about the clip itself or the audio quality, and so on. So similarly, if we think about images or videos, again, highly use case driven. If it is videos for training autonomous vehicles, for example, right? There is a lot of emphasis on what objects are there on the streets, right? So now you can have a silver table just for objects, and then you have another table for the quality of the video files and so on. So there are a lot of there's no set standard on, okay, this is how I'm going to decide. It's all very dynamic. And
go ahead.
And to wrap that up, like a lot of feedback comes from once you train the model also, because at the validation stage, be like, oh, okay, my model is not doing well with stop signs, so let me go back and do something about stop sign.
Okay. So in terms of you, I like how you actually framed it. It's very dynamic, because you can't really know ahead of time how somebody is going to ask you a particular question. You have to be dynamic and you have to be adaptable. And I think one of the important bits is the flexibility of the medallion architecture. You can go back to the bronze and change your queries to generate the silver tables. So this was done on a frequent basis as you were incrementally building the pipelines to final goal stage. You were constantly changing the number of silver tables and subsequently the number of gold tables at the same time, correct?
Exactly. Yeah.
Okay.
And that's the nice part about Delta Lake, right? It allows for schema evolution.
Yes.
Backability. So there's a lot of flexibility there.
Yes. And how much of that flexibility and how much of that schema evaluation, deletion vectors, all those stuff that Delta Lake actually offers, including some aspects on Iceberg as well, did you guys use during this particular pipeline? I mean, can you give me one instance where you had to, the data changed quite a bit and you had to delete the data, or the new metadata came in, they had to add the data? What was the way you approached that?
So So like I said, the good part about Delta Lake is it allows for seamless schema evolution, but in a lot of times we had to just start from scratch, and more often than not, it happens very frequently, whether we like to do it or not. We don't want to completely rebuild the whole silver table or the gold table.
Right.
We don't want to do that. It's very expensive, computationally very expensive, very time consuming, and if you think about the personas who actually are the end users of the gold tables, right? They don't have too much knowledge about the medallion architecture, for example. So there needs to be data engineering experts who can rebuild these tables. But it is quite often. I don't have a number to quote, but it happens all the time.
And in terms of the frequency of the ingestion, how often it happened? Did it happen like an hourly basis that the data was coming in from this disparate distributed storage, or was it towards the end of the day? How often was the ETL pipeline built? Or it actually depends on, okay, we've done the first batch of the ETL pipeline. Now we're actually going to train. Once you're trained, we're going to test the model to see the validation of the models, and then we're going to go back and do the new ingestion. Or was it actually happening in real time? Can you give us an idea what was the nature of that?
Actually, it's so if you think about it, right, there is batches of data that come in, whether you get it from the vendors or from open
Right.
source,
Right.
which is the raw data, right? And from raw data, there is endless possibility of generating synthetic data.
True.
So raw data comes in chunks, but synthetic data, it's kind of it keeps flowing. It never stops, because it depends on how much you want to spend at the end of the day, how much compute you have, how much storage you have, and you can keep on generating and keep on perfecting your models.
So I'm assuming most of the use cases for this particular ETL training data were deep learning images for vision recognition.
Audio.
Yes.
A lot of this is actually for fine tuning, because we
Yeah.
have the foundational models for each speech, audio, speech, videos, and so on, like Cosmos. And then on top of that, you fine tune them for very specific use cases like warehouse operations, or training robots in some harsh environments, or specifically training or improving AV model for some road signs, etc.
Right. Now, you mentioned a lot about the heterogeneous architecture of both the Rapids, allowing you to have a Spark cluster that have both CPU and GPU at the same time, and you were using both resources to do some aspects of data processing, and then the more deep learning training model, you actually were doing GPU. But you also mentioned something that you were also using GPU to do data processing as well, right? How did you decide what aspects of the data processing would benefit from doing the accelerated GPU as opposed to standard CPU? Was there any particular factor within the metadata you determined, I think if we were doing this, if you wanted to process this sort of metadata, it makes actually sense to use GPU and not CPU? Can you give an example of one of those instances?
Yeah, actually, if you think about that medallion architecture, where we want to consume from the queue or from object store,
Right.
The first stage is building that bronze table, and bronze table is kind of just a pass through. It's like
Yes.
read as quickly as possible, no transformations, not many Spark operations. All you're doing is just reading from source and writing to a sink in delta format. So there, we mostly use CPUs, because either it's a streaming job, or there's not much Spark operations going on, so GPUs may not benefit so much there.
Right.
But the subsequent stages where you have merge or some transformations, filtering involved for silver tables and gold tables, that's where GPUs will accelerate a lot, especially the gold table part, where you have numerous joins and animations, and also the analytics part where you retrieve data from gold tables. Those are the stages that will greatly benefit.
So anytime we're actually doing a Spark operation that requires merging group by large operations that actually requires a lot of shuffling, that's when you would attribute, or you would assign that to GPU.
Right. Yeah.
Now we mentioned, or you showed a couple of slides where you were actually comparing the queries that you were running against. There were a lot of SQL select statements and select from this table, that table, and so on and so forth being emerging, and you compare the latency of each of those. Were those run against the Delta Lake tables, or was it somewhere else?
Yeah.
They were run again, and they were run against the gold tables, not silver.
Yes, exactly.
Okay, so this was run against a pristine gold table in Delta Lake, where you actually do that.
Yeah. What's really surprising is the amount of metadata. We were not expecting it to be so overwhelming in petabytes.
Really?
Yeah.
Okay, I think we actually might have. Let's see if you actually have a question from LinkedIn. Let me see. Yes, there's a question from Sudhakar from LinkedIn, where he's actually made about 30 to 40% of the company's exclusive tech giants in large number of workloads still store data in gigabytes rather than terabytes and petabytes. For an organization with relatively small data set, how does GPU acceleration provide an advantage for training and inference. In these cases, couldn't they achieve a similar performance using traditional CPU-based architecture?
Yeah, I think this is the small data problem with GPUs, right? And yeah, we have observed this too. That's one of the main challenges working with GPUs is how, how how fast we can retrieve data from storage and feed that to the GPUs, and then how many operations you will do on the GPUs. So if you're retrieving very small amount of data from the GPU, from the storage to the GPU, and if you are processing, if the number of operations on GPUs, yeah, it probably does not accelerate too much. Again, it depends. Like even if you have a small data set, if you have a lot of window aggregations or percentile computations, it's still uh, faster than CPUs itself. So it's not more of I have only gigabytes of data. Will it help? It's more like you need to look at both size of the data set from storage to GPU and also the number of operations you perform on the GPU, and that's
Right.
how you can decide whether you want to go with a CPU or a GPU.
Okay. Yeah. So it depends on the queries
Yeah,
that determine whether you're going to use CPU and GPU.
right.
Another question that comes from Sandeep from LinkedIn: how do you folks think about purging for data that is outdated, since it is a large amount of data? I think it's probably talking about how did you actually maintain? Did you run vacuum? Did you run deletion on frequent basis? How did you determine what data is outdated to remove them, so that way your versioning tables in the table remain small, rather than all this clutter that you carry around from one table to the other?
Yeah. So, this has been a big challenge for us, all the while, like which to determine which data is important, right? We are trying to establish some patterns. Okay, if some data is not used for certain amount of time, can we tier the data to uh, 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 like low costing storage, low cost storage solution, right? And then worst case we can retrieve from there. There will be a latency, but still okay.
Oh.
The main challenge itself is there's no established pattern, and that creates a problem. Uh, so, so we are trying to build some sort of a tiered storage where okay, we want to run vacuum continuously. That way, at least the number of files does not grow too much, and also it helps with the cost reduction on one side. But to delete or purge the data itself, we need to come up with some custom ways, heuristics, working with
Yeah.
each case uners,
Yeah.
each use cases, and then decide, okay, we're going to implement this rule. Anything that is not used for 90 days, we're going to just move it to another tier, store in that tier for a year, and then just purge it.
So coming up with a strategy, just like caching, where you have time to live, and if
Yeah.
nobody has access to that particular data, you
Yeah.
push it out to a tier storage. Another question: you mentioned something about you have various lake houses. How many different lake houses do you have? I mean,
Yeah.
or was it just a flippant reference to various lake? But I
So-
mean, there's one lake house. They actually have this entire workflow that you had. That's layered architecture. But in addition to the, would you consider the tiered architecture, where you actually have redundant data or unused data, as part of another lake house, or there's something more specific and significant about other lake houses?
So at least here at NVIDIA, we operate across different regions, different CSPs, and also NCPs like CoreWeave, etc. Uh, and if you think about it, in some cases, we want to have some sort of data locality where the data is co-located with compute as well. And also for compliance reasons, we cannot pull data from some of the data centers. So in that case, we'll be operating with multiple lakehouses that are local to that CSP or region. So yeah, I think that's where the challenges are, and that's why I said, okay, there are multiple lakehouses.
We have another question from a LinkedIn user about data churning. In data churning workflows, or data curing workflows, not churning necessarily, Is the processing typically done in place on the original storage, or is the data copied to another location for queuing and then moved back to the original storage after the process is complete?
Yeah, so there are two parts to this question. One is the raw data on the object store, which is needed for building the fine-tuning data sets for training. And then there is the Delta Lake data on object store. Generally, we don't move the Delta Lake data on object store at all. We try to spin up the compute as close to the Delta Lake as possible because we are looking for low latency queries, right? So copying is not an option. However, with training, we have some leeway, although it's kind of we don't prefer it. We have to move data from object store to something like a fast storage like cluster, and the cluster can be mounted on hundreds or thousands of GPUs for training for faster access. I have not seen anybody train so much directly from object store, but rather they prefer moving the data from object store to Lustre. Generally, we don't move the data back to object store. Again, it depends on use cases. Every time a new data set is created, an object store as source of truth, and then copied to Lustre temporarily, and then the data is destroyed.
Out of curiosity, you talked a lot about doing deep learning training. What frameworks are you using? Mainly PyTorch for doing
It's
model training?
predominantly PyTorch, and I have not seen much of TensorFlow. Yeah.
I mean, given that the Open Lakehouse supports both Delta Lake as well as other lakehouses such as Iceberg, and there's a lot of now similarity in terms of the functionality and the Data Lake and Iceberg are sort of merging together to make sure that they're completely transparent, interoperable. The user is probably curious to know if you actually do that in Iceberg, could you do it too?
Oh yeah, actually, Spark Rapids acceleration works on Iceberg seamlessly, similar to Delta Lake.
Okay, brilliant. Well, there's your question. I mean, to me, both are very similar, and I think we'll reach a point where they'll be very, very much interoperable. Let's see, what other questions do I have coming? I think I don't have any more. We have answered almost all the questions, and I think you answered all my questions that I had. But thanks a lot for your time, and thanks a lot for all the people who actually joined. If you have any more questions, we have about a minute or so left. Plug in. You can actually take the last question for the end of the year. But if not, wish you guys all happy holidays as we are approaching. This will be our last Open Lakehouse series for the year. Hope to see you again next year. So thank you for attending, and thank you, Narijan, for showing and sharing the insightful way how you actually do use Apache Spark and Rapids. Oh, one more question that popped into my mind. Yes. Last for the day. You mentioned something about serverless, right? You have your Rapids architecture that actually does serverless. Are you guys presumably using Spark Connect to allow using the serverless effortlessly?
Yeah, so that's a good question. Actually, we are currently using QB. We are yet to transition to Spark Connect, and I'm very excited to transition to Spark Connect. To be honest, it has a lot of great features, but currently we are actually using QB.
Okay, well, good to know that. Delighted to hear about your future plans, and thanks a lot, Nirjan, and thanks a lot.